Good afternoon, everyone. Thank you for joining us today for DataBytes with the National Consortium for Data Science. My name is Jayshu Jagannatha, and I lead communications efforts for the consortium. Today, we're so excited to welcome back Chris Lam for Causal AI, the key to high-stakes decision-making. Before we get started, I'm going to share a few housekeeping items that will just make the entire experience easier. We have disabled Zoom chat and Q&A for attendees. We've disabled these to allow Chris to present without distractions. We do offer a place, however, for you to share your questions and comments. All questions and comments should be uploaded to Easy Retro, which is our crowdsourcing Q&A platform. I'll share the link in the Zoom chat now, and we'll share instructions and the link before we begin the Q&A. If we don't get to your question during our session today, we will address it in our wrap-up materials. And with that, I'm going to give it over to Chris.
Thanks, Jayasri. So let me share my screen. 1 second. Okay, can you see my screen?
Yep.
Okay, perfect. So first of all, I'd love to thank Jayasri for inviting me back to give a presentation on to NCDS on Causal AI. Which I believe is the key to high-stakes decision-making. So last time I did a presentation on a theory of fairness, and I thought for this presentation that I would just be able to present a collection of ideas about causal AI that I developed in developing this theory of fairness that I presented before. So let's begin. So now, as we all know, everyone is right now trying to ride the generative AI wave. And I would like to argue that I think there's another hidden AI wave. So the thing about generative AI systems is that they're not designed to address many problems in AI ethics. And in fact, they may even amplify problems in AI ethics. But we have this new approach to AI called causal AI, that is actually designed to address many of the problems in AI ethics. And if we can address these AI ethics problems, then this will enable us to be able to use causal AI for high-stakes decisions, as opposed to generative AI systems, which are optimized for low-stakes decisions. So what do I mean between low-stakes versus high-stakes decisions? Well, when we think of generative AI, we think of low-stakes decisions like chatbots or image generation. But causal AI is optimized for high-stakes decisions, so things like risk modeling or regulatory policy. So I know there's a lot of discussion, for example, in Washington, D.C., about how do we regulate AI systems so that they're aligned with the policymakers' goals and with society's democratic values. So the thing is that there's currently a lack of trust in today's AI systems. So you might have heard that there's 3 different types of analytics. There's descriptive analytics, which tries to describe what has happened. So when companies, for example, start their analytics journeys, they start with descriptive analytics. So this could include things like business intelligence, building dashboards, reports, describe what's happened in the past. And then companies eventually move to predictive analytics, hiring data scientists to make predictions about what could happen in the future. And then the final stage of analytics, the most advanced stage, could be considered prescriptive analytics, which is trying to describe what should we do, how should we make a decision so that we could achieve some type of business objective, for example. Now, the difference between predictive analytics and prescriptive analytics is that predictive analytics is more focused on passive observation, so correlating past data in order to try and make a prediction about what's going to happen in the future. Whereas prescriptive analytics is more focused on active interventions. How do I make an intervention into a system in order to achieve some type of business objective, such as maximize profit? And the thing is that there's been this type of wall, a brick wall between predictive analytics and prescriptive analytics. So even with the generative AI systems that we see today, most AI systems are within the predictive analytics state. And where we want to go, if we want to build AI systems for advanced analytics, is to go to prescriptive analytics. So the question is, how do we jump this wall? Now, there's a fundamental flaw in how we build AI systems today. If you imagine that this tower represents AI systems, you could imagine that generative AI is about making this building taller. So adding more data, more compute, more complex algorithms. But the thing is that as this building gets taller, we notice there's something wrong. Okay, we're seeing issues around fairness, transparency, and trust. And these issues existed before, but they're getting amplified. And I would argue that the reason why is because the foundation of this building is built on a weak foundation of correlation. If you think about how AI systems are being built today, it's about correlating a bunch of variables with each other. So if you could think of generative AI as kind of the equivalent of trying to make this building taller. And causal AI, on the other hand, is about addressing the foundations of this building. So moving from correlation to causation. So it's very different approach to AI systems than the way people are focused on AI systems today. Now, the thing is, to fix the foundation, to build a better foundation for AI, we need to change its representation. So remember that the shift from analog to digital in consumer electronics was this huge shift. It unlocked new capabilities. By taking an analog signal and converting it into a digital signal, we unlock certain capabilities. We could do error correction, recreate perfect signals. We could do data compression, send more data within its channel. And we can also increase security to prevent eavesdroppers from being able to intercept a signal. And I believe that we're going to see a similar shift in artificial intelligence, that this is a paradigm shift moving from correlation to causation, which will also likewise unlock new capabilities. So imagine moving from neural network representations of machine learning systems to causal representations like a causal Bayesian network, that this is going to be key to being able to unlock things like building great improved fairness, transparency, and robustness in AI systems. Now, one thing that I want to drive home with causal AI is this idea that AI systems have different layers of abstraction. So imagine you have this block diagram here, where you have this black box, which is your neural network. And what you do in machine learning today is you feed it in a bunch of data, and then it renders some type of decision. So in credit, for example, it might be to approve or deny a loan. In hiring decisions, it might be to whether to screen out a resume. And the question is, what about this protected attribute? So this protected attribute could represent something like race or gender. How would you use this in a black box neural network? Should you even use it? That's been a big question that has perplexed all of the AI researchers. But what if we took this black box and instead we represented this as a causal Bayesian network? So this is, if we do that, what we have is something that could be like this diagram. So here we have a causal Bayesian network with 5 nodes. A represents a protected attribute like race or gender. W represents a mediator, which it depends on the application. But for example, in credit, it might be credit worthiness. In employment decisions, it could be workers' qualifications. And so A causes W, and then W can then cause both X. X is the data. For example, data about the person applying for a loan or applying for a job. And W can also cause W, an outcome. So for example, whether someone defaults on a loan or some employee churns from a company and leaves the company. The data X, so W can create data X. X can then be used to create some type of decision Y hat. And your neural network is embedded inside this node. And the decision Y hat can also affect the outcome as well. And we have discussed this in my last presentation on fairness. And the thing is that the same information in this block diagram is represented in this causal Bayesian network. And the nice thing is that once you have it in this format, now you unlock new tools for being able to modify a machine learning system. So now, for example, in case of fairness, we can model, for example, different forms of bias, which is represented by the color of these different nodes and edges within the graph, as well as different forms of fairness. We can model, for example, fairness to unawareness, where the protected attribute A is not used in the decision Y hat, or fairness to affirmative action, where the protected attribute A is used to modify decision Y hat in an affirmative manner. We can also use this to model different forms of discrimination. So we could model, for example, overt racism, covert racism, or reverse racism. So this representation is very powerful for dealing with issues of fairness. Now, the thing is that decisions of the past could represent data of the present, or also decisions of the present could represent data of the future. So what we could do is we could take a decision, the decision leads to some type of outcome, and the outcome could then be fed in as as future data. So we want to be able to think about how, for example, historical discrimination could lead to disparities across groups in the data that we see today. So we want to be able to model this type of feedback loop. The thing is that, so if we wanted to do that in a causal Bayesian network, it might look like something like this, where we take the outcome Y, and then it will be fed back into the mediator to generate new data X. The thing is that if you do that, then this is no longer a causal Bayesian network, because a causal Bayesian network is a directed acyclic graph. That is, it's acyclic. There are no feedback loops. So this is no longer a causal Bayesian network. So that's a problem. But what we can do again is we could play the same trick, and we can model this whole thing as a causal loop diagram. And if we do that, we might get something that looks like this. So here we have a causal loop diagram where you have two feedback loops, two reinforcing feedback loops. And this causal loop diagram is called the success to the successful archetype, if you're familiar with system thinking and systems dynamics. So let's say that we want to compare the success of two different groups, group A and group B. And we want to use that to determine an allocation of resources to A instead of B. Let's say, for example, you start in a system where group A is more successful than group B. Then the system may decide to allocate more resources to group A than to group B. So A gets more resources, and therefore A becomes more successful. B gets fewer resources, therefore B becomes less successful, and the whole thing repeats again. And now you can kind of see why this is called the success to the successful archetype, where a system that, for example, is doing fairness through unawareness and just looking at the success of two groups may then blindly allocate resources, and therefore the rich get richer, the poor get poorer. This is also called the Matthew effect. So now what we can do is we can then replace these nodes in this causal loop diagram with the nodes X, Y hat, and Y. So if you remember the causal Bayesian network, we had these variables. X represented the data, which is your success between group A and B. Y hat is your decision, which is being made by your neural network, which then leads to different types of outcomes for group A and B, Y. And then this thing feeds back into itself. So basically what a causal Bayesian network is in a way, it's kind of like X to Y hat to YA, and then you chop off this edge over here so that there's no feedback loop here. And then this is kind of like two causal Bayesian networks. And so again, same representation. We were able to represent the same information using different diagrams. Now, and what this means is that these different types of models, neural network models, causal Bayesian networks, and causal loop diagrams, they're all related to each other. And in fact, we can think of them as a causal loop diagram can contain causal Bayesian networks can contain neural networks, and as a result, they're kind of like a series of Russian nesting dolls. And the main insight is this idea that you can use one analytical technique to analyze another analytical technique. Previously, we used to think that these were three separate techniques that were independent of each other, but they're not independent of each other. They actually are related to each other. So what does this mean? Well, it means that we can then improve how we understand things like causality. So there's this book written by Judea Pearl. He was a Turing Award winner with basically a Nobel Prize of Computer Science, who wrote this book, The Book of Why, and I highly recommend that everyone read this book. But in this book, he describes this idea of a causal ladder, okay? And the causal ladder has three different layers. The first layer is association. So it's associated with activities like seeing and observing, and it asks questions like, what if I see blank? And questions like, how are the variables related? How would seeing X change my belief in Y? And it's examples of questions that you might want to ask is, what does a symptom tell me about its disease? What does a survey tell us about the election results? So this is all using association or correlation, and this is not causal. the next two layers are causal. So intervention, which is layer 2, involves doing and intervening. So ask questions like, what if I do blank, or how? What would Y be if I do X? How can I make Y happen? So now you're starting to make interventions within a system. And for example, if I take aspirin, will my headache be cured? Or what if we ban cigarettes? And then Yuta Pearl proposes that there's a third layer within the causal ladder called counterfactuals. And this involves activities like imagining, retrospection, and understanding. So this you might ask questions like, what if I had done blank and why? So was it X that caused Y? What if X had not occurred? What if I had acted differently? So the main difference between intervention and counterfactuals is that intervention is more about, okay, if I make an intervention now, what do I predict is going to happen in the future? Whereas counterfactuals is more about, what if I made an intervention in the past? How would that affect where I am in the present? So it's more backward looking and trying to be more retrospective to understand how things happen. And this is the most advanced level within Yuta Pearl's causal ladder. So it asks questions like, was it the aspirin that stopped my headache? Would Kennedy be alive if Oswald had not killed him? What if I had not smoked for the last 2 years? But I make the argument that Yuta Pearl's causal ladder is missing a layer. So imagine if we instead create a new causal ladder. So layer 1 is the same. So we just changed association to correlation. It's pretty much the same. And this represents the field of supervised machine learning. And this could be represented through things such as a neural network. And these things are very good at prediction. Layer 2 is linear causation. So if we take these two layers, combine them together, and this layer represents causal inference as defined by Yuta Pearl. The representation of this is a causal Bayesian network. So you have this directed graph, and the applications for this are really optimal for decision making. And then I would argue that there's a third layer called nonlinear causation. So whereas linear causation has a start and an end, nonlinear causation has a feedback loop. And this is represented by the field of system dynamics as pioneered by Jay Forrester. It's represented by causal loop diagrams. And the main application in causality is simulation. So how do you get from layers 1 to 2 and from layers 2 to 3? So as I showed before, to get from layers 1 to 2, you have to think outside the black box. And then to get from layer 2 to layer 3, you violate the DAG constraint of causal Bayesian networks. And this idea, and as a result, you have these 3 different layers. Each layer has its own different unique behaviors and properties. And this idea that there's different layers which have different properties is part of this larger idea called emergence. That if you think outside the black box, what emerges from a neural network is a causal Bayesian network. And if you violate the DAG constraint, what emerges from a causal Bayesian network is a causal loop diagram. And more specifically, this might be considered weak emergence. Now, in terms of causality, we could think of linear causation as being more of the algebra of causality. And if you've heard of Yuta Pearl, he also talks about Duke calculus, but I would argue that this is all part of algebra of causality, the algebra of causality. Whereas system dynamics, Jay Forrester's work, is more like the calculus of causality because it's much more dynamic, whereas algebra is much more static. We can also, if you've read the book Thinking Fast and Slow by Daniel Kahneman, there's a lot of talk among AI researchers about the role of system 1 versus system 2. And I think that system 1 is more associated with the bottom layer, supervised machine learning, neural nets, for example, where you need to be able to make a snap decision. Whereas system 2 is more related to system dynamics, where you're able to run simulations within your mind in order to be able to think slowly about certain types of problems where you just can't make snap decisions. Now, this is all part of this broader field called systems thinking, which is this idea of, again, that you have different layers. Each layer has different properties and behaviors, and then you have emergence that allows you to move from one layer to another. And within systems thinking, we can think of the top half of this ladder representing complex social systems, whereas the bottom half represents complex technical systems. So this idea that there's social systems and technical systems and understanding the interaction between the two is going to be very important if we want to build AI systems that can be trusted in society. So for complex social systems, symbolic AI is really good for modeling things like the world to capture causal representations of how things behave in the real world. So that's where we think the top half is representative of symbolic AI, and this bottom half is more representative of machine learning, which could include, for example, with LLMs, foundation models. So hopefully this allows you to see how lots of different ideas in AI can be bridged together using this new causal ladder or causal hierarchy. But let's talk a little bit more about symbolic AI versus machine learning, because that's a central debate in AI that I think with all the hoopla with generative AI, it's been and machine learning, there hasn't been enough attention paid to this. You can think of causal AI as a hybrid of symbolic AI and machine learning. So whereas machine learning is more optimized for processing data using complex algorithms in order to do things like correlation, symbolic AI is very useful for being able to leverage knowledge and reasoning in order to be able to build AI systems and represent them using symbols. Now, what do I mean by knowledge and reasoning? Because I think there's been a lot more attention to data and algorithms than what knowledge or reasoning means. So let's start with knowledge. So how does knowledge relate to data? So there's this idea called the DIKW pyramid, where the bottom layer represents data, the next layer is information, then is followed by knowledge, and finally wisdom. And in this pyramid, this representation, we know that there's a lot more data in the world than there is wisdom. Actually, there's very little wisdom in the world. But now the thing is that data represents factual information, such as measurements or statistics, that can be used as a basis for reasoning, discussion, or calculation. Information is data that has been organized or formatted so as to be intelligent and intelligible and useful to us. Knowledge is the fact or condition of knowing something with familiarity gained through experience or association. So for example, being able to associate the causal relationships between variables is considered knowledge, not data or information. And then wisdom, which is the rarest of them all, represents a wise attitude, belief, or course of action. It could represent good sense or judgment. And the idea here is that we want to be able to move up this pyramid in order to make decisions that are more high stakes. And one of the things that we might want to think about with the difference between knowledge and wisdom is that knowledge can capture intuitive relationships, causal relationships within the data. Wisdom, on the other hand, may capture counterintuitive relationships, which are rarer, but allows us to see things that might be what we consider wise, that is not clearly obvious. Otherwise, that would be part of knowledge. So the idea is that to move from predictive to prescriptive analytics, we need to move from data-driven decision-making to knowledge-driven decision-making with some wisdom sprinkled in. Now, the field of systems thinking requires us to integrate knowledge across fields. And there's this ancient parable that helps explain system thinking called The Blind Man and the Elephant. And it's a story in which it talks about there were a bunch of blind men that were having an argument about what an elephant looked like. And the emperor invited them in to be able to invite these blind men to be able to feel different aspects of the elephant in order to be able to resolve the dispute as far as what an elephant looks like. And one blind man sitting on the top of the elephant was feeling the elephant's ear and concluded that an elephant was like a fan. Another blind man was touching the side of the elephant and concluded that an elephant is like a wall. Another blind man was feeling the tail of the elephant and concluded that the elephant is like a rope. This blind woman was feeling the leg of the elephant and concluded that the elephant was a tree. This blind man touched the trunk of the elephant and concluded the elephant's like a snake, and this one concluded that it's a spear. So what happened during this exercise was that because the blind men were only touching one aspect of the elephant and they couldn't see all the aspects of the elephant, the blind men didn't resolve their dispute. They were still arguing, except this time one's arguing it's a fan, the other's arguing elephant's like a tree or a spear. Now, let's say we wanted to replace this elephant with a very, very special type of elephant. And let's call this elephant the elephant in the room. So we put this elephant in this room, and let's talk about, one particular topic which could be considered an elephant in the room problem, which is the fairness problem. And let's give each of these blind men an occupation. So this blind man is a philosopher, this one's a sociologist, this one's an economist, this one's a politician, this one's a lawyer, and this one's a computer scientist. And now, each of these different professionals are going to be arguing different aspects about the fairness problem. So for example, the philosopher might be arguing about the role of free will versus moral responsibility. The sociologist might be arguing about the role of structure versus agency. The economist might be arguing about the role of capitalism versus socialism. The politician will be arguing about left-wing versus right-wing politics. The lawyer might be arguing about the role of disparate treatment versus disparate impact. And the computer scientist might be arguing about the role of symbolic AI versus machine learning. And the key here with systems thinking is being able to understand all of these different perspectives and being able to integrate them into one unified whole. So this is an introduction to systems thinking. Now, and LLMs actually can help humans with this because we're not all professional philosophers or sociologists or computer scientists. So LLMs can definitely help with us to being able to integrate all these different ideas together into a unified model. So now let's talk a little bit about reasoning. So it's commonly accepted that there are three main types of reasoning. There's deductive reasoning, inductive reasoning, and abductive reasoning. So let's use an example that I'm sure everybody has heard about for deductive reasoning, the idea that all men are mortal, Socrates is a man, therefore Socrates is mortal. So this is an example of deductive reasoning. It's very logical. We know this is true. Inductive reasoning, what we could do is actually take this example and make some modifications to it. So we could say, for example, let's say Socrates is a man, Socrates is mortal. And then we also look at, well, we know Plato is a man and Plato is mortal. And we know Aristotle is a man and Aristotle is mortal. So we have lots of examples of all these ancient Greek philosophers who are men, and they all happen to die. So we know they're all mortal. And then we conclude from this information that all men are mortal. So this is an example of inductive reasoning, using lots of examples to come to this conclusion. Abductive reasoning is a little weird. So compared to deductive reasoning, let's say that all men are mortal again, but let's say that Socrates is mortal, and therefore we conclude that Socrates is a man. So that's an example of abductive reasoning, which is a little weird because this statement could be wrong. For example, the truth might be that all men are mortal, Socrates is mortal, but Socrates is a dog. Okay, so someone may have named a pet Socrates. But at least the statement is still better than saying Socrates is a rock, because we did say Socrates is mortal, and we know that rocks are not mortal. So we could represent this using a bunch of directed graphs. Note these are not causal graphs, so don't assume there's any causality here. But we could say that if Socrates is a man, if Socrates then man, and if man then mortal, then we could conclude if Socrates then mortal. And this statement in deductive reasoning is always true. It's logically deduced given the axioms, like a mathematical proof. So in this case, though, we say if Socrates then man, if Socrates then mortal, and we have other examples like Plato and Aristotle, and then we conclude that if man then mortal. And we conclude that is probably true. It's statistically concluded given the data, especially if we have enough data using some type of statistical test. On the other hand, here we say if man then mortal, if Socrates then mortal, then what we're doing with abductive reasoning is we're saying if Socrates then man. And we conclude that this could be possibly true, but we want to basically choose the best explanation given the data. So this is called, this could be used in hypothesis generation, although some people conclude these are actually hallucinations. So the thing is that to be able to generate these explanations, we want to apply Occam's razor. So when faced with two possible explanations, the simpler of the two is the one most likely to be true. So what we can do, though, is that if we have a hypothesis that Socrates is a man, we can use this to think about, okay, what additional data do we need to collect in order to get this arrow to look more like this or like this? So for example, we could say, well, we know if Socrates, then Greek male philosopher, if Greek male philosopher, then man, then we conclude Socrates, if Socrates, then man, which is deductive reasoning. Or we could flip the direction of this arrow and we say, oh, if Plato's teacher, then Socrates, if Plato's teacher, then man. And we have other evidence, like if Sophroniscus' son is Socrates, his dad is Sophroniscus, and if Sophroniscus' son is man, then we can conclude that Socrates is a man using inductive reasoning. But we have to be careful to make sure that we don't find an example where somebody else named their pet Socrates. So Socrates did not refer to just this one person, but multiple objects, in which in that case, then clearly Socrates would not be a man. So we have to be a little careful when you're using inductive reasoning. So you can think of symbolic AI as more along the lines of deductive reasoning. You can think of machine learning as more working along the lines of inductive reasoning. And causal AI is a combination of symbolic AI and machine learning, so using deductive and inductive reasoning. But we also need to be able to reason about using abductive reasoning, So using all three forms of reasoning in order to be able to think about how these AI systems work. Now, I also would like to say that we can acquire knowledge from different sources. So for example, if we say that the bottom is correlation, so this is statistical models, that's one source where we could generate knowledge or acquire knowledge by correlating data with each other. We also can acquire knowledge through what I call strong causality, so things like randomized experiments. Okay, so but there's also this other type of causality, which I call weak causality, which is through mental models, so models that we build of the world within our head. Now, correlation, statistical models, is heavily exploited by data scientists through machine learning. Randomized experiments is heavily exploited by real scientists who are using the scientific method to derive knowledge. But on the other hand, this type of causality, mental models, has been largely ignored by scientists, both data scientists and real scientists. And the thing is that, so strong causality, randomized experiments, is the gold standard for causality. But oftentimes, it's difficult to establish due to cost or ethical reasons. On the other hand, these statistical models raise multiple AI ethics issues. They may require large amounts of data, and they may be brittle. So I want to encourage people to start looking about mental models, weak causality, which may enable you to build trustworthy systems if, and that's a big if you can get the models right. Just because it's hard to be able to build good mental models doesn't mean that we shouldn't use them. We should definitely use them within the data scientist toolkit instead of just relying on just statistical correlation or randomized experiments as ways to generate knowledge. Now, one way to think about these differences in how we work with these two forms of causality is that randomized experiments works along the lines of scientific thinking, so empiricism, versus mental models works more along the lines of systems thinking, so using rationalism. So rationalism versus empiricism, leveraging both approaches in order to acquire and generate knowledge. And this is, again, largely been untapped by the AI community. Now let's pivot over to explainable AI, because causal AI also has applications here. Now, there's been always a long-standing debate over whether to use model agnostic methods, such as LIME and SHAP, which try to interpret what's happening inside a black box, versus using interpretable ML methods. Like here's an example of a two-layer additive risk model developed by Professor Cynthia Rudin at Duke University, which is a glass box model. And there's this debate between whether to use a black box or a glass box model to explain AI systems. If we were to represent this using block diagrams, again, we have this black box neural network here versus this glass box additive model here. But what we can do is with causal AI is that we could combine this with SHAP. So we could take this black box neural net, use SHAP to explain individual decisions, but then we could also use causal Bayesian nets and causal loop diagrams as higher level abstractions, which are glass boxes, to provide better explainability into this black box model than just using SHAP alone. And what that means is that we still get many advantages. There's many advantages over using purely interpretable ML models. First is, of course, because you're not replacing the black box, these things are easy to build. Second is that, so that's the same with SHAP as well. But what we get in addition is that these causal models provide high-level abstractions that are easier for humans to read, and that's because they're intuitive. Causal explanations are naturally more intuitive and may even expose counterintuitive behavior, especially when you start using causal loop diagrams and systems thinking. And finally, certain classes of problems like fairness, bias, and discrimination can only be modeled at the causal levels. You can't model these topics by using SHAP or using glass box models like additive interpretable ML models. So one of the main ideas points that I want to drive across is this idea that unifying different AI fields may enable new breakthroughs. So if you think about DeepMind, what they were able to do is they were able to combine Monte Carlo tree search with neural networks to build AlphaGo, which delivered superhuman performance in playing games like Go. And what my company is doing is we're trying to combine neural networks with causal Bayesian networks and causal loop diagrams in order to build more trustworthy algorithms. And hopefully this will get us one step closer towards a grand unified theory of AI. So now we're closing near the end, and I want to argue that the next major wave of AI is hybrid AI systems. So actually, the DARPA, the Department of Defense, likes to talk about this idea that there's multiple waves of AI. And if you think about the first wave of AI systems, it might be like symbolic AI systems, so like examples of expert systems. And these systems we know never performed very well. So as a result, they were replaced by the second wave, which is the machine learning wave. And we see things like deep learning and generative AI. So my belief is that the next wave is going to be hybrid AI systems, these third wave AI systems. Examples of this include neurosymbolic AI and causal AI. And we need to get to this wave of AI systems before we can get to artificial general intelligence, which is the final wave, which, as Professor Pedro Domingos describes in his book, is the master algorithm where you unify all the different AI techniques together. So with that, here are some great references if you guys want to learn more about causal AI. So Pedro Domingos, for example, wrote this book on the master algorithm, talk about how to unify different AI techniques to build this, this general AI system. Daniel Kahneman wrote the book Thinking Fast and Slow, which describes System 1 and System 2 thinking. Eric Larson wrote the book The Myth of Artificial Intelligence, which talks about the different forms of reasoning, deductive, inductive, and abductive reasoning. Gary Marcus wrote the book Rebooting AI, which he made strong arguments that you needed symbolic AI to build trustworthy AI systems, which I wholeheartedly agree with him. Donella Meadows wrote the book Thinking in Systems, a great primer to systems thinking. Guido Pearl wrote the book of Why, which is a great introduction to causal inference, and then Causal Inference in Statistics, which is a very good introductory textbook in causal inference. And Peter Senge wrote The Fifth Discipline, which also talks about systems thinking and system dynamics, and talks about different types of archetypes. So I think that's my presentation, and I look forward to any questions that the audience might have.
Thank you so much, Chris.
Mhm. You're
All
welcome.
right. Yeah, we are going to move over to the Q&A portion. I will begin sharing my screen and go over some instructions for that.
Okay.
Yeah, so as you might have seen in coming in the chat, there was a link to our Easy Retro board. I will drop that in again. To add your ideas, please click the plus sign in the relevant column. We have a few columns with different topics that Chris has addressed today. Type your idea, hit the blue box with the thin white check mark, and save within the same field. Your idea will appear up on the screen for our reaction. And you will also be able to upvote someone else's idea using the thumbs up icon on each of these little messages. And you can also comment on an idea using the quote bubble icon. And now let's maneuver over to our Easy Retro board. Chris, I'll let you take it away.
Okay, great. Let me take a look. So I see the most upvoted one is, can you give examples of concrete problems this is good at and concrete problems causal AI would not work well with? So definitely some concrete problems that causal AI will be very good at. So as I mentioned earlier before, risk modeling, I think, is one of the killer applications for causal AI. So if you work in financial services, which is highly regulated, I mean, a lot of the most advanced AI techniques are only being used for back office applications, like automating customer service or doing things like fraud detection, but things in which are activities that receive high levels of scrutiny, for example, like using AI for credit or insurance underwriting. Companies are generally quite afraid of using that, and that's because to be able to use that, you need better theory, and that's where causal AI plays an important role. Another area that causal AI is going to be very fundamental for is an AI policy. So the thing is that the purpose of causal AI, what causal AI can do is it could help you to be able to translate the requirements from policymakers into legal and technical specifications. That's basically your policy that can be understood by data scientists who can use those specifications to build mathematical code such that you have AI systems that are compliant with the law. So the problem is that all of the AI experts who are currently advising policymakers in Washington, D.C., not a single one of them knows how to use causal AI to apply to policy. So that's an area where I think people who are watching this presentation, this is an area that you guys should really take a close look at if you want to pursue policy positions in AI policy, because this is an area that's very fundamental to AI policy and that none of the experts that currently are advising policymakers in DC know about. So causal AI might not work well with certain types of applications where you can't build a good causal model of the problem because the models are very complex, or problems in which they're just low stakes applications in which you just can get away with just doing correlation, in which then there's really no need to do all this additional legwork to build causal models of the problem. You could just do statistical correlation and curve fitting. So I think those are, hopefully that answers your question. Let's see, next question. I agree, Book of Why is great. Can you recommend a comparable wide audience book about symbolic AI? That is tough. I can't think of any. Well, I guess a good wide audience book is the Gary Marcus book. So Rebooting AI. So that one gives a high-level overview of symbolic AI and why it's needed for building trustworthy AI systems. On the other hand, in terms of good textbooks, I think it's hard to find good symbolic AI textbooks. It's just AI researchers haven't been focused heavily on that area. What other questions? How does causal AI relate to other efforts to build ethical AI systems in industry? So a lot of the work on building ethical AI systems currently are around areas like, for example, building certifications, doing audits, building risk management frameworks. And while those are all necessary and important, I would argue that they're not sufficient for building ethical AI systems, that we also need to have much more rigorous mathematical theory on how these AI systems interact with society. And those techniques have been largely unexplored by AI researchers as of yet. Although hopefully with presentations like this, there will be more interest in investigating causal AI. What other questions? What do you believe are some of the most promising applications for causal AI? As I mentioned before, applications around financial applications, highly regulated applications like risk modeling, also in employment applications, for example, in screening resumes, in which you have to deal with natural language processing and ensuring that those systems are not biased or discriminatory. As well as problems in which involve business decision making. So for example, I think in logistics, inventory planning, if you can build a good causal model of that problem, then you can use that model to modify a machine learning system to be able to make decisions that are more trusted. Let's see what other questions have been uploaded. Otherwise, I can let's just go through some of these other questions. I have been learning about causal DAGs and Unipearl's work, but I didn't see a way to delve into causal loop diagrams. Could you tell me how to learn more about it? And then, yeah, so I would highly recommend, there's a website called www.thesystemsthinker.com. And that was a website that gives an excellent free introduction on how to work with systems thinking, how to use causal loop diagrams, as well as to work with more advanced systems thinking methods like stock and flow diagrams. And then, let's see, I actually had a lot of questions about systems that may not be perfectly represented by DAGs, so I'm glad you brought up loops. Hope this helps. Is there a method to mathematically estimate the strength of causal relationships in loops as there is in causal DAGs? So a lot of this is going to be in like running simulations. So being able, for example, to build a causal loop diagram, converting it into something that's called a stock and flow diagram, which is a more concrete mathematical representation. And then you could then be able to feed that stock and flow diagram within a tool like Vensim, and then use that in order to be able to run simulations. And those simulations can then be able to start generating some mathematical numbers for you to understand how the dynamics of the system work. So that's what I would, that's one way to apply mathematics to this. What are some good references for learning about systems thinking? So as I mentioned before, www.thesystemsthinker.com, as well as a book by Donella Meadows called, I think, Introduction to Systems Thinking. I listed that before, as well as Peter Senge's book called The Fifth Discipline. How does causal AI contribute to creative thinking? I will leave it up to the generative AI people to focus on creative thinking. So I think causal AI, I mean, there is some creativity in terms of building causal models of the world, in which you have to be a bit creative in terms of figuring out what are the nodes that you want to include in your causal model, what levels of representations, in order to be able to model the system and to get it quite right. So I think that could be an application to creative thinking, but I mean, I think generative AI is really optimized for being able to create new thoughts. What is the best way to reach me? I'd love to talk about causality. So my email address is chris@epistam.ai. And you can also find me on LinkedIn under Chris Lam or Christopher Lam, and just look for my company's name, Epistamai. Okay, how do you think about the incorporation of human preferences? Are there instances where preferences are inherent in the model, or is it just how we use the output of models? How might we account for heterogeneous preferences? So, actually, I did a presentation on fairness before, in which we discussed, for example, differences in preferences between, say, left-wing and right-wing policymakers in terms of what is fair or unfair. And the idea here is that if you can encode those preferences as like a series of causal graphs, So you take the knowledge that you have about the world and then encode it as causal relationships and into these causal graphs. Then you can use those causal graphs to then understand, for example, how to build a fair system in a fair machine learning system. So being able to incorporate certain preferences of different types of policymakers. But I'm sure it could be applied to other things, for example, different requirements, for example, of business executives for achieving certain types of goals. So the key here is how do you model that as a series of causal relationships? Because once you have a good causal model, then you can connect this to a machine learning system. Could causal AI do something like image classification? I think that image classification is really a deep learning type problem. So I would say, yeah, it's probably better to use deep learning for image classification. Causal AI is more useful for decision making as opposed to like prediction problems, like predicting what class an image belongs to. Okay, how does one design and train a causal AI system? Are the causal loops designed in advance or discovered through training? So the design and training a causal AI system, I only touched on this very, very lightly in this presentation. So if you remember the causal diagrams of fairness through unawareness and fairness through affirmative action, in which I just showed you whether or not to use the protected attribute or not. So actually the work of designing and training a causal AI system is more complicated. And actually we also have a couple of patents on that area. So if you want to learn more, please feel free to reach out to me, yeah, be more than happy to talk about how you use how to train a causal AI system. And then second, are the causal loops designed in advance or discovered through training? So the work that we're doing is to design the causal loops in advance. So there's a lot of work in causal inference and machine learning where you're basically, for example, using machine learning to enhance causal inference to find what those causal diagrams look like. And this is typically what social scientists do. They try to determine causality from the data, but what we're doing is instead we're saying, okay, if we already have knowledge, from our mental models of the world, we can build those mental models, and then we can use those mental models to build these causal diagrams and then represent things like the supervised machine learning process. And then we use the insights from that causal diagram to then design and train an AI system. Yeah, we design them in advance, but it's not. But you don't have to. There's probably other ways to do it to discover them. I think there's a lot of work, for example, in causal discovery. So being able to take data, detect if there's like independent relationships among the data, so that at the very least you could show that there's conditional independencies within the data. So it could help you to then identify those causal relationships. But the problem is that there's limitations in what the data can present because the data doesn't tell you how the data was generated, and it can only tell you if it's independent. It can't tell you, for example, the direction of causality. If A causes B or B causes A, it can only tell you, for example, if A is independent from B. So that's where being able to use knowledge and reasoning using mental models of the world can help with being able to build those causal loops and those causal diagrams. Let's see, are the slides available to view and reference? I think Jay Asri said that we're going to be posting these slides in the presentation on YouTube. And then I'm sure, yeah, we could make a copy of the slides available to everyone who attended this presentation. Any other questions? Otherwise, I think we're good. Let me check the chat.
Amazing. Well, thank you so much, Chris, for your time today and for your great presentation. Oh, actually, I think we had one more question pop up. Is that correct?
Oh, is there another?
Sorry, no, I think something got moved around. It's such a great tool. It just does things automatically.
Okay.
But again, thank you so much for your time today. And thank you everyone for attending. We do have a brief evaluation that we ask our attendees to fill out. The link is up there, and I will also share it in the chat right now. These evaluations really help us with future programming and figuring out how to bring topics to you that you all would like to see. Additionally, we are looking for DataBytes speakers for 2024. So if you're interested in becoming a DataBytes speaker and sharing some of your work with the larger National Consortium for Data Science audience, I really encourage you to consider filling out our interest form, and we will get back to you on that if you do. As it's the end of the year, I just want to give everyone a heads up to please keep an eye out for future programming. Like I said, we have DataBytes that will be starting up back in, I think, February, along with our spring career panel will be held sometime around then, as well as our Data Matters Spring short course series. We have not announced the dates yet, but we will be doing that soon. And I encourage you to visit datamatters.org if you're interested in learning more. Thank you all again for attending today, and a big shout out to Chris for sharing this presentation. And we will see you in the new year. Thanks, everyone.
Thanks, guys.